In this video, we will explain concepts relating to momentum, such as the law of conservation of momentum, impulse, and 4 types of collisions. I will talk about the 4 types of collisions. So you have magnets on magnets, which is like a elastic collision with similar poles, where they go like that without touching. This will be explained through a lab, by the way. And you have a total inelastic collision where they collide and stick together and keep moving at the same speed. An inelastic collision is like that, except they don't move together. They kind of break off, but still keep going in the same direction. And an explosion is when they start at rest, but get launched away from each other.
So at this point you may be asking yourself, what really is momentum? Well, that is what I am here to teach you. The literal definition of momentum is the amount of movement an object has, which can be measured by multiplying mass and velocity. This results in units of newtons per second, which will usually be what is denoted by P, which is momentum. Momentum is a vector as it has a direction because of the velocity, which is denoted by the arrows over velocity and momentum. It also has a magnitude, which makes it a vector. Another important thing to note about momentum is that it is dependent on reference frame. So if you're on an airplane, it may not seem like you are moving, it may not seem like you have momentum, but to an observer on the ground, you have quite a bit of momentum. Another key concept of momentum is the conservation of momentum, which is an equation that states in an isolated system, the final momentum of the system should be equal to the initial momentum of the system. So to show that, we will have 2 objects which are pushing on each other. We would denote this by force. The force of object 1 is equal to the opposite of force of object 2, since Newton's third law states that every action has an equal and opposite reaction, and they're pushing in opposite directions. In this system, the gravity and normal force cancel out, as the objects are not falling through the ground and they're also not floating. So as we know, that means the net force is only equal to the force of the objects pushing on each other, which is net force is mass times acceleration. So we can substitute that in for both forces, giving us these 2 sides of the equation. And 2 is to denote object 2, 1 is to denote object 1. And as we know, acceleration equals the change in velocity over the change in time. So we can substitute that in for acceleration on both sides here. And with the change in time, the 2 objects are moving with each other, so you are able to cancel out. You're able to cancel out the time on both sides, which leaves you with this equation. And then you can substitute in final velocity subtracted from initial velocity, or initial velocity subtracted from final velocity, as that is what the change in velocity means. That is what this triangle means delta. And then you can distribute the masses on both sides, which leaves you with this equation. Then you want to add the 2 variables that are negative on both sides, so then you have only positive variables, and that leaves you with this. And as we know, momentum equals mass times velocity. So what you want to do here is you want to substitute in momentum for all the masses times the velocities, which gives you the final momentum of object 1 plus the final momentum of object 2 equals the initial momentum of object 1 plus the initial momentum of object 2. And as we know, there are only 2 objects in this system, so adding their 2 momentums gives you the final momentum and the initial momentum of the system, which is denoted by this. And now we have solved the conservation of momentum, and which again states that in an isolated system, the final momentum of the system is equal to the initial momentum. In both of these demonstrations, you can see the use of the conservation of momentum. In the first demonstration, the rubber band ball is rolled into the basketball. And the conservation of momentum is seen here when the momentum of the rubber band ball is transferred to the basketball as it hits it. This is seen when the basketball moves as the rubber band ball hits it. So the momentum of the rubber band ball was transferred to the basketball. In the second demonstration, when the rubber band ball is held on top of the basketball and they're dropped together, the basketball hits the ground first, and then it transfers the momentum it gets from the ground, and this is the impulse, which will be described later. It transfers that momentum into the rubber band ball, causing the rubber band ball to bounce much higher than it would have normally if it was just dropped.
Now let's talk about impulse. Impulse is equal to force times the change in time. In the units for force is newtons, while the units for time is commonly seconds. So the unit for impulse is going to be newtons times seconds. Another thing is the impulse momentum theorem. This theorem states that impulse is equal to change in momentum, which with this figure out that force times change in time, which is impulse, can also be equal to mass times change in velocity, which is change in momentum. Now, in regards to the video of the ball dropping, the ball will drop with a constant velocity, which is 9.81 meters per second. And just before it hits the ground, the instant before it hits the ground, it will have a certain momentum. This momentum simply being the vector of momentum equals mass times the vector of velocity. And right as the ball hits the ground, there will be an impulse, and this impulse is just normal force times time. The normal force being mass times gravity, so it'll be however heavy the ball is times 9.81 times the amount of time it spends on the ground, which in this case is a very short amount of time because it's a ball. It's going to hit the ground and then bounce right back up.
In this lab, 2 cars are set on a low friction track. Motion detectors are set up at either end, allowing us to measure the velocities of each of the cars as they move along the track. Upon acquiring the initial and final velocities of each car, we are able to find the momentum of each car before and after the collisions. One key observation is that the greater the mass of the car, the greater the momentum, as momentum equals mass times velocity. Now that we know the initial and final momentums of the cars before and after the collision, we are able to calculate the impulse acted on each of them. The impulse is equal to the final momentum, being momentum after the collision, subtracted by the initial momentum, being momentum before the collision. Using this system, we are able to find the impulses applied on each cart. Another way of finding the impulse is by using the force exerted on the cart multiplied by the time the force is applied. This can be done by finding the area of the triangle created when a force is applied in a collision on a force versus time graph. The resulting impulse is the same value it would have been had the other method been used. To example these claims, one trial of our experiment can be observed. 2 carts are thrown into each other in an inelastic collision, one having mass of 0.7534 kilograms and the other having mass of 0.2517 kilograms. The initial velocities of each cart was 0.39 meters per second. After the collision, the greater mass cart has a velocity of 0.053 meters per second, and the cart of lesser mass has a velocity of negative 0.359 meters per second. Going through our calculations explained above, we can find the impulse acted on the greater mass cart to be negative 0.2539 newtons per second, and the impulse on the smaller cart to be negative 0.1885 newtons per second.
Thanks for watching, and I hope you are now a momentous man for others.